In this video, we're going to solve a problem which involves an inductor and a resistor. So mostly the idea is about a current decaying in a circuit here. So in this case, the switch A, here is in position A. So that means this circuit is completed here. This circuit is completed, and it is again for a long time. The idea of long time here is that the current in this circuit will be a constant, or a steady current is passing through this circuit here or through the inductor here. So here long time doesn't necessarily mean that it has to be about like a day or 2 days. It can be 1 second depending upon the value of L and R. So 1 second, 2 second could be a long period of time. So then after a long time, once this switch has been in long time, we throw the switch to the position B, and then what will happen, then we'll have a new circuit and the battery will be disconnected. Then we have to find out what is the maximum current and how long does it take for the current to get to this value, or what will be the current in the circuit after 10 microsecond and 10 millisecond, and how long does it take for the current to decay to 5% of its maximum value. So let's do this one. Okay, so when the current, or when the switch is in the position A for a long period of time, then that's the circuit. Forget about a B at all. Don't think of B at all. There is no R2 component because it is disconnected. And now in this case, when the switch is in the position A for a long period of time, then this inductor simply behaves as a wire, as a zero resistance wire, or as a short circuit here. So it will simply behave as a short circuit here. These two terminals will be simply short circuited here, or just as a conducting wire here. Okay, because after a long period of time, the inductor will no longer resist. Okay, it will resist initially, but after a certain period of time, as there will be a steady current, then there will be no resistance, there will be no opposition by the inductor, or there will be a steady current in the circuit, or as there is no change in the magnetic flux, there will be no EMF induced. So in other words, in simple words, after a long period of time, this inductor will simply behave as a conducting wire. So that means if you look carefully, then we have a battery. Just take a look. Whether we have a battery here, and then we have a resistor, and this is simply a wire. Then we can find out what is the current in the circuit here, and this current, that will be the maximum current, is given by this EMF divided by R1. We're not taking this one into account because this will be simply behave as a wire here. Okay, all right. So I max will be epsilon divided by R1, or this is the potential difference of the battery, which is 20, and this is the resistance 50 ohm. So this is the current in the circuit when the switch was in position A. Now once we connect the switch to the position B, so let me draw the circuit here, or I'm going to draw the circuit here, and then you can understand a little better here. Copy, let me paste here. So now what I'm going to do, I'm going to make some certain changes here. So when the switch is connected to position B, so that how it looks like, then you see then that there are two resistors in series, and then there is an inductor here, and there was a current. And remember, what was the direction of the current? The current was passing this way initially, but now once the switch is connected to the B, the current starts decreasing. The inductor hates that changes. Inductor doesn't like to change this. It doesn't like to see the current decreasing. So what it will do, the inductor, it will produce an induced current. So the direction of the induced current will be in this way. So that will be the induced current direction, because the current starts decreasing. So in order to counter that, the induced current will be in this direction here. Okay, and in order to happen that one, this term must be positive and that term must be the negative. Okay, so that's all the circuits we'll now look for here. So let's find out the time constant of this one. What is the time constant? If you remember the equation, the time constant is L over R. What is the value of L, or what is the inductance? The inductance is 5 millihenry. So 5 times 10 to the negative 3. And R value, if you look at the resistance value, we have two resistors here, 50 ohm and 150 ohm, and they are connected in series. So what is the total resistance? The total resistance is 200. Okay, so we get a time constant, and that time constant I should have calculated here. So that's the time constant here. Okay, L over R, and this is the time constant, 2.5 times 10 to the negative 5 second. Okay, so now when the switch is in this position, the current starts decreasing, and that is the equation we have here. If you remember in the last video when I talk about the LR circuit where the current is decreasing, that was the equation for the current. Now all you have to do is plug in the value of time equals to 10 microsecond. That's what it is asking. What is the current in the circuit when a time equals to 10 microsecond and 10 millisecond? So that's what I'm doing here. I'm simply plugging in this circuit the time equals to 10 microsecond. We already got, and this is the I0, which is the maximum current in the circuit, and the maximum current in the circuit we have got is 0.4. So this is also I0 here. That's the maximum current in the circuit. So this is 0.4. Exponential t value, we have to find out the current in the circuit at 10 microsecond. 10 microsecond means 10 to the negative 6. And we got the tau value, which is the time constant, 2.5 times 10 to the negative 5. That's what we have. If you solve, then you will get 0.268 current. Okay, the maximum current is 0.4, and after 10 microsecond there will still be a current in the circuit, but it will be slightly lower, 0.268. And now at 10 millisecond, if you solve it, then this value is approximately 0. You see here that long period of time here also means 10 millisecond is a long period of time for this kind of circuit. Okay, so there will be no current in the circuit here. Okay, that's how you find out. All you have to think about here is how does the inductor behave. That's all you have to think. Okay, so now if you come back here again, so if you look at this equation, then at time equals to 0, the time equals to 0, this inductor or here at 0 equals to time, this is simply behaves, this there will be the maximum current, so this will be simply behaving as a short circuit, and as a time after a long period of time the current is 0, that means it behaves as an open circuit or as a disconnected from the circuit, and that's the reason we got 0 ampere. So the inductor at the time equals to 0 behaves as a short circuit, and after a long period of time it behaves as an open circuit for a current decay. All right, so this is it from this video. If you have any question, please write out down in the comment section below, and thank you, and I will see you in the next video.